Good morning. So we're talking about friction and ideal surfaces. So we have two blocks, and hey, do they have the same acceleration due to friction? So if you look at it, we have acceleration is going to be equal to the force divided by the mass. And so when it comes to the opposing friction, um, so whatever the force is, it could be an FA somewhere. But the friction opposing is going to be mu sub k times mg. And because the mass is in the bottom, the masses cancel, and it doesn't matter. So like it could be a force this way, and it could be friction this way, right? So Fk could be going that way, and Fa is that way. So it really doesn't matter the mass or the weight of the block. However, that's an oversimplification. In physics, we often do that. We use ideal springs. Hooke's law, for instance, it works like this, but then it basically, after a certain point, the spring actually breaks, right? So you can't just like go forever with this with the distance of a spring. We got force versus distance, the stretch of the spring, and we get Hooke's law, which is that ideal, but it's ideal range. And so it's same is kind of possible. It's true with the physics of friction. So the physics of friction talks about these two surfaces that are sliding across each other, and we get the mu sub k as a result of the idea between um, the forces between these two surfaces. But if you get, let's say you take a wheel, and let's just say you turn it into like some sort of a wedge like this, it's going to dig into the ground. It's going to literally dig into the asphalt, and you're not going to have the same mu sub k. So the mu sub k is going to change, right? So that thing is going to change. I mean, like, what is the definition of mu sub k? Mu sub k is the interaction between the two surfaces, and so in ideal circumstances, this is true. We'll go green for true, right? So in ideal circumstances, this is true, but that's only in ideal circumstances. Um, let's talk about your tire of your car, right? So there's the road, right, and then you have your tire, and then we have like racing flats are really wide, and so why do racing flats that are really wide? Why do they give better friction, better contact with the road? And it has to do with the fact that almost like being destroyed. So this is going to destroy the surface. Well, the interaction between the molecules of the road and the tire here, they can actually rip away. So, ripping away the molecules is different than sliding over the top. So as it rips away, it leaves rubber on the ground, right? And so that interaction makes it much more complex than just this idea of that friction, either Fk or Fs, is equal to this coefficient of friction times the normal force. I mean, in an ideal situation, we're talking this is all good, right? But the problem with physics at a AP1 level is that we literally have to set this up as ideal. Like for instance, we always say ice is frictionless. Ice is not frictionless. It's just we're trying to set up an ideal situation so an AP physics student can answer the question. I think that that bleeds over into real life, and that's the danger sometimes when physics students don't talk about the repercussions of real life, because real life is where real stuff happens. And if you're assuming we can make these dumb statements, and what I mean by that is the dumb statements is that in all cases this is true. We will hear people arguing this is true. No, this is not possible. If you increase the surface area, it doesn't change the friction. If you increase the mass, it doesn't change the friction. It's simply not true. It's true under ideal circumstances. And so um, when you don't stretch those boundaries, then it's definitely a good rule that works under circumstances where you're not stretching the boundaries too much. A good way to say it would be like, would a block that's different shaped, right? Would it if you slide it across a surface like this or like this, would it make a difference? And under ideal circumstances, it wouldn't. And the reason why is because the downwards pressure on it is a result of the area, right? So as the area gets less, the pressure gets more, and it basically balances out. It's this idea that these factors will balance out, and that is true. The factors do balance out. The one on the top will balance out the one on the bottom. And you'll see that in many cases. But there are limits to where this happens. If this one is going to actually destroy the surface, then it's going to have more friction than this one, even though they're the same mass. If they slide over the surface and they don't destroy the surface, then it should be the same amount of friction, because the masses cancel. But surface area can come into play when you're talking about whether or not the surface is going to degrade. Brakes, the same way with brakes. If brakes heat up, right? So the inside of your brakes, you have these pads, right? And those pads, they're actually made wider in bigger tires because they'll dissipate the heat. So bigger wheels will have this um, um, wider surface area, and it dissipates the heat. And so if you're pressing the brakes, you can get what's called brake fade, like when you're in the hills. And brake fade, when these bad boys heat up, they'll lose their molecules. And so the friction between the two, the mu sub k, will change. And so you might say, well, it doesn't change. Well, mu sub k definitely um, does change. There's another thing that we don't consider is this is considering weight. It's not considering like the reason a brakes work is because it's not weight, it's pressing against something. And so when you have a disc brake, it's squeezing together. And so people talk about like, well, can I change the mu sub k um, by doing different things to it, by adding different elements, by thinking of different aspects of how we can change the friction, and that's true. So going back to this is ideal circumstances. It just um, I think for regular physics, it's good to know the rules and to look at ideal situations. But at the same time, students have questions, and those questions are true. And sometimes we just wash over them, and we don't address them because maybe we'll confuse somebody. So I don't think it's confusing actually to say that if we put things under ideal circumstances, then the equations work perfectly. But as you go through real life, just try to kind of consider that it may not be exactly this way. It may be a general rule, but there are many things that are more complex than we can approach in this class. So it's kind of fun to think about, actually. So I appreciate people that think in those ways and bring up those questions. And you should never leave those questions unstated. You should always try to search out what is the answer to my questions, because they're excellent questions. Um, so anyway, interesting topic, and I hope you had fun trying to answer the friction questions. But anyway, there goes my 2 cents for this morning.